Let's say you want to put a spacecraft in orbit. What do you need to know to be able to put that spacecraft in orbit? Well, first you need to know your planet, in this case Earth for us, and then you need to know the basic orbit that you will be going into, which here I've drawn a ellipsoid orbit, but the main parameters that you need for the ellipsoid part is the semi-major axis, which that's the major axis divided by, or major axis split in two. So this is the semi-major axis right here, which is denoted A. Now, after you have that, you need to know your eccentricity. Now, eccentricity is a tricky thing, with the technical definition being the sine of the angle of the ellipse in the conic section. In the conic, it is divided by the sine of the angle of the conic. But there's an easier definition, which is the linear eccentricity divided by the semi-major axis. Now, the the linear eccentricity is the point from one focus, which is supposed to be your planet, but I drew the planet wrong. So we'll consider that to be one focus, and then we'll consider over here to be the other focus. Now, if you know your distance from a planet, you can determine your linear eccentricity, or if you know your semi-minor axis here, which is B, then you can do that. Now, for the semi-minor axis way, it's a squared minus b squared equals c squared. So, a squared minus b squared equals c squared. And c is the linear, let's see, c is that whole line there. Now, you can do it that way, or you can just determine the distance from, once you know the distance from the planet to one of your apsides, which is, there are two apsides. Your bottom apsides, your lowest point in your orbit is the periapsis, and the highest point in your orbit is your apsis. Now, you can use those distances to determine what it is. So in that case, if you have your periapsis from the center of your planet is like 5 or something, then you can just subtract that from your semi-major axis to get your linear eccentricity. And then to get your regular eccentricity, E, you divide C by A. So that's eccentricity. Now for orientation, that's a bit more difficult. Well, not more difficult, but requires a few more variables and 3 dimensions. So, in terms of, actually for the first part, I can just do it in 2 dimensions. If your orbits are on the same plane, so generally for your 3 dimensions, you do the equatorial plane. Let me see if I can draw that. If you have another ellipse, say, that is your equatorial plane, a slice of the equator of your planet, and you say the actual equator of your planet is like that over here. Then, and then your regular orbit is like that. Then you can get the inclination and different things like that. But for now, we can just do this. So for determining the rotation of the orbit in its own plane, you get... Actually, first I need to go over here and do it this way. And then I can show that way, but then it won't be. First, you need to know when you're going north and when you're going south in your orbit. So for demonstration purposes, that will be the ascending node. And that's denoted... Well, no, actually, so... That will be the ascending node, and then over here you can have your descending node where it crosses that plane over there, and then that's across there is the line of nodes. And then let's say that actually up here it doesn't look to be very eccentric, but say this is your periapsis, and then so now that you have your ascending node, you need to pick a reference direction for your longitude to get your longitude of ascending node. So you could pick this direction or this direction or this direction, doesn't really matter. It's just you have to have some fixed location. What I've read has said the vernal equinox is used, so I'll just choose this point here. Now then this will be the line connecting, that will be the longitude, and then this will be here the vernal equinox. So if you go around here, that angle is the longitude of ascending node, which is denoted omega, something like that. So that is one angle, and then you have the argument of periapsis, which is from the, which determines the thing here, which I'll just use this for an example. So let's say your ascending node was like this way, and your periapsis is here. That your argument of periapsis would go around like this, or this, go around like that. And that is the argument of periapsis. Now, which is denoted by a sort of squiggly W. Now, the other thing that you need is the inclination. So inclination is just the angle from the plane, reference plane, the equatorial plane, to the plane of the orbit. So you go from there, that is I, for inclination. And so now you have everything except one bit. You need the true anomaly, which is the, it's the angle, so, true anomaly is the angle from your current location in your orbit, like, say, over here, that's where your spacecraft is, and then you would go from your periapsis around to where it is, there. So, or actually it would be from the center of the equatorial plane, which would be there, so it would be more like that, I think. Anyways, I think it's the same angle. But that's, which all of these together make the Keplerian, named after Johannes Kepler. So, K-E-P-L-E-R, Keplerian orbital elements. And this is my video for the Khan Academy Breakthrough Challenge.